All right, guys, we're going to go ahead and get started with our sound and light test review. Watching this is going to help you do a great job on that test, get a high grade, and just simply perform well. All right, so we're going to go ahead and just go question by question, addressing each of these on the review sheet that you should have a copy of. So the highness or lowness of a sound is going to be pitch. You could also put frequency here because frequency determines the pitch of that sound. Here you have an example of a concave lens, and you can think of this as being like a little cave. It has that shape. As light comes in, it's going to be moving out through this in that format. So understanding that we have those two different kinds of lenses and just kind of knowing the general activity that they'll have on light is something that you're going to see on that test. You want to make sure you're familiar with both of those and just how they kind of affect light. And just so you know, just kind of going back, this concave lens is light travels in this direction, it's going to separate outward like that. All right, why does sound travel faster in liquids than gases? And that's because the particles, let me rewrite that, particles are closer together. Remember that in a solid, they're very close together. In a liquid, they're a little bit further apart because they're moving faster. And then in a gas, they are highly separated. So you're always going to have sound travel fastest in a solid, slowest in a gas. Which section of the human ear gathers sound waves? Let's see, outer ear. Okay. Blink is used to locate objects underwater by reflection of sound waves. That'd be sonar. So sonar is used by, you have a boat that's on top of the water, kind of floating around, and it emits a sound wave that goes down. It can hit something like, let's say you have some buried treasure here, and then it reflects back, and they can tell how deep something is, how far away it is. Looking over here on this diagram, this is a convex lens. So if you had a laser, like you have a little light here, you want to turn that into a laser, you can shine your light through a convex lens, and that will cause all the light beams to focus on one central point. Okay. Again, light's coming in from this direction, and it kind of focuses, it gathers together into one very concentrated beam of light. Why do you hear a firework before you see it? Great question. I love this. I like to use the example of lightning for the same example here. And the reason for that is that light travels faster than sound. Light is about 300 million meters per second in a vacuum, and sound is like, I think it's like 300,000 meters per second. So sound is still pretty fast, but nothing even like, light is exponentially greater than sound. A wave bending around a barrier or an opening is going to be diffraction. Just kind of looking at an example of that. Let's say you had two little walls here, and you have the wave come in, and it's going to hit this. It's going to kind of move outward from that point. And another example would be if you had a wave hit like a central barrier, it would separate into two different waves as it hits this little block right here. If you had that in the ocean. But that's just showing you, and all you have to know about it is that it's generally going to bend. Now, sometimes that diffraction can lead to constructive or destructive interference, but That's what's pretty much going on. The change in pitch or wave frequency due to a moving wave source is called the. So here's the thing, guys. The source can be moving or you can be moving, either one. But when we have a apparent change in pitch or frequency of a sound wave, that is known as a Doppler effect. This can also happen with light waves too. We can have white light appear to be certain colors or change the color because there is movement. That's how we can kind of use telescopes to determine how far away stars are and whether they're moving closer to our galaxy or further away. So we can actually use the Doppler effect to help us. Light rays converge when they pass through a blank lens. That converging that I was talking about earlier, well, I didn't really use the word converging, but I'll go ahead and get there. Converge means to come together, right? And so that's going to be a concave lens. That means coming together. All right. So when the siren's coming closer to you, let's go ahead and go to number 12. I know I'm going out of order here, but when it's moving closer to you, the sound waves are compressed, which means you have a high frequency. So that's going to be a high pitch. So high pitch is going to be approaching you. Okay, moving away from you is going to be elongated. So you're going to have those sound waves move apart. So you now have a lower frequency. And that's going to be a lower pitch. Okay, so the pitch gets low, whereas with compressed waves, the pitch gets high. All right, number 11. Light and sound waves, how are they classified? Okay, so let's just kind of, there's a couple of classifications here. So sound is going to be mechanical and longitudinal. And light is going to be transverse and electromagnetic. Now the general overall difference here is with electromagnetic waves, you are not going to require matter for that wave to travel. It can travel without a medium. It can act on its own accord and does not need a medium to travel, which is good because it needs to travel in a vacuum in order for that sunlight and the warmth of the sun to reach the earth. All right. Primary pigment colors are going to be CYM or cyan, yellow, magenta. That's going to be right here. Now, you know, if you have a printer at home, your printer is going to use these three colors as well as black. So if you actually look inside your printer, you're going to see these color codes to help you. But these use subtractive colors. So each of these pigments will absorb light. And the one that's not absorbed, the one that's reflected back to you, is a cyan for cyan, which is a kind of a deep blue color. It looks a little bit like this color. You know what yellow is, and I don't have the color on my palette right now, but this is pretty close to magenta, although it's a little more pink. But with those three colors, you can actually make all the colors that you need to print on your printer just using those. Okay, here's some yellow added there too. Let's go ahead and go to the next question. An object will appear blank when it absorbs all color and black. Black is the absorption of all color. Conversely, white is reflection of all colors, all wavelengths of light. So when I say color, that's essentially a wavelength of light or How we see color, we are perceiving frequencies of visible light. Okay. Which lens is used in a magnifying glass? That's going to be convex. It's also used in microscopes. And telescopes, because basically, if you think about it, all of these have the same functionality. Basically, you have something that's really small, and you're making that little small object, there's a little insect you might be observing with a microscope or magnifying glass. So it makes the little object appear larger. Now, if you look at what I drew before with a little diagram, remember I said, hey, if you shine a light through it and make a laser beam like this, well, think of it like this. This is the object, and you're looking at it, and it's doing this. It's going through the lens, and so that's why it appears to be larger for you. Plastic wrap is transparent, and explain what happens when white light passes through a prism? Well, what happens is when light goes through the prism, it is separated into the different colors of the spectrum. We have red, orange, yellow. Where's my yellow? There we go. Green, blue, indigo. That's this deep blue color right here. And then we have violet. So basically, this white light comes through and just gets separated. All right. What is white? What does a white object appear white? It is reflecting all wavelengths. And when I say wavelengths, I'm also referring to frequencies of light. Describe pitch. Which property determines the pitch of a sound? It's going to be frequency. And we already answered this, but basically it is the highness or lowness of a sound. So an instrument like a tuba makes a very low pitch sound, whereas an instrument like a flute makes a very high pitch sound. So the pitch of that sound is determined exclusively by frequency. So this is also, if I were to ask you what determines the color of an object, it's going to be the light that is reflected, and it's going to be what the frequency or wavelength of that light is that determines what color it's going to have. What would happen to light as it traveled through a liquid and then a gas? It is going to refract. And the reason for that is because you have different media. And then the next question, all lenses can bend light. So remember that concave lenses are going to bend that light outward, whereas convex lenses, that's horrible, let me draw that again, are going to bend light inward. Now, when we have microscopes and telescopes, like I mentioned those before, something to kind of throw out here is that you're going to have both kinds of lenses. You're going to have that convex lens to make the object bigger, but you're also going to have a concave lens to help you focus so that you can see better. And that concave lens is usually really minor and not very powerful at all. It's just on like the little eyepiece, but we have both of those. This question, you're going to have resonance. So if you have a tuning fork and it looks like it's a piece of metal that looks like this, and you use this to make sure that the piano sounds right. So you basically have this little tuning fork, you hit it on an object, it begins to vibrate, makes a little sound, and it will happen if a certain note is played like correctly on a piano. Like if you hit the right note, it will cause this to vibrate. What do boats use to navigate and find their bats? Sorry, bats use echolocation. Now this works just like sonar that I mentioned before. But you have the bat, a little bat right here. There we go. And little bats like flying around. And what it does is it kind of like sends out like a little sound wave. And if there are some mosquitoes, they eat a lot of mosquitoes, like 40,000 a day. Basically, the sound will reflect back, and the bat's like, okay, there's some mosquitoes over there, so it'll fly over and it will gobble up the mosquitoes. But again, it's using a sound wave. Like it'll make a little sound wave, listen for it to come back, hear that echo, and then it will know where certain things are. And that's how they survive. Tracing paper is an example of a translucent material. So it allows you to see some of the object underneath, enough for you to be able to trace. But it's not completely transparent. It's actually really difficult to make paper that would be completely transparent, but it is translucent. So guys, just so we go through this. So transparent means you can see through it and all light passes through. Translucent means some light passes through. Opaque means no light passes through. Number 26 is going to be amplitude. So the loudness of a sound, how loud it is in decibels, remember we measure that in decibels, is going to be related to the amplitude of that sound wave. Volume, the word volume actually means size. And so like when you are listening to your music, if you turn the volume up, you're basically making the sound wave larger. That's a good way of kind of thinking about that. List the colors of the visible spectrum in order from greatest to least energy. So guys, remember that frequency relates to the energy of a sound wave. So we're going to have red, orange, yellow, green, blue, indigo, and violet. And that is low energy to high energy. And these are the frequencies, right? So remember, you know, like if you go above violet, you get to ultraviolet. That can actually cause skin cancer because it's so like, you know, high energy. All right. So the difference between regular reflection and diffuse reflection. So regular reflection is just going to be one angle, whereas diffuse reflection, you're going to have several angles. Again, it still follows the law of reflection, but you have several angles that are happening because the surface is not completely flat. Which sound wave is going to be louder? The larger. It's going to have greater amplitude. And because of that, it's going to be louder. Why must there be a medium for sound to exist? Because it is a mechanical wave. I apologize for the handwriting here. It's difficult to write with a stylus. Refraction and diffraction. So refraction is different media. Whereas diffraction is going to be barrier or opening. Interesting fact here, even though light does not need a media to travel, it can be affected by media. Media can slow it down. And media is plural for medium, which is just matter, solid, liquid, or gas. A person who is blind can see objects, distant objects clearly, but can't bring nearby objects into focus. So a person that has this going on is farsighted. Now, I am actually the opposite of this. I'm actually nearsighted. So without my glasses, I can very easily read, but I cannot see things that are distant or far away. So I definitely need to wear them when I'm driving, but not when I'm reading. All right. What happens to light when it hits an opaque object? It creates a shadow. So the light might be absorbed or it might be reflected. The idea is light is not transmitted, does not go through it. So it's going to block the light and it's going to create a shadow. I'm going to rewrite the word shadow here. That looks so bad. There we go. Shadow. All right. Law of reflection, what does it state? It states that the angle of incidence, that means the source of the light, equals the angle of reflection. There we go. All right. Next question, we got number 35 here. We've done a lot today. A blank uses two convex lenses to magnify small closed objects. Really, you could put a couple of answers here. So magnifying glass is what I would put. But also, I mean, honestly, a microscope pretty much does the same thing. Now, of course, it's a little more complicated, but it's true. Blank objects do not allow light to pass through them. That would be opaque. Opaque does not allow light to pass through them. All right. All the following would cause a diffuse reflection except what? So brick would, leather would, like if a shiny black leather jacket is going to reflect some light. Glass could, you know, if it's not like, I mean, you could have like broken glass, I guess, but glass really would not. Fabric, I think fabric would probably absorb most of it, but if you had some fabric that could reflect, it would, because it's kind of like rough, especially if you don't have it laying flat. So this is not really the best question. It's a little confusing for me because I'm not sure exactly what type of glass, what type of leather, what type of fabric. You could do different things with materials. The only one that I know is definitely going to cause some diffuse reflection is a brick, because you really cannot make a brick too smooth. You're limited in how smooth you can make a brick just because of how it's formed. So, I mean, honestly, I think glass, especially if it's flat glass, is just going to be plain reflection. But fabric, if it's laying flat and it's reflective, it could emulate the glass. So it's a complicated question for me, but maybe I'm just overanalyzing it. The distance from the center of the mirror to the focal point, right? So this is not something that we're going to encounter a lot. But, you know, I do want to go ahead and make sure that we have kind of like, you know, introduce you to it at least. So that, you know, if it does ever, and it just kind of extends your learning anyway, but I'm not sure if this is something that you really need to know, but we're going to call that the focal length. And it's not complicated. You know, you're talking about distance and focal, so it's going to be the focal length. All right, let's go ahead and go to our last here. Blank is the only part of the electromagnetic spectrum we can see, and that would be visible light. Visible light. Now, you know, if it says we can see, that literally means the word visible. And electromagnetic spectrum is just another fancy word for light. Primary colors of light: red, blue, and green. With those three colors, you can pretty much make any color of light that you want. It's not overly difficult or challenging, but you can certainly do that. Thank you for watching the video. Make sure that you take some time to study, prepare yourself. We want to see everyone do a great job on the test. Thank you so much.